Assalamu alaikum everyone. This is Fahd Ansari and I'm here to help you conquer chemistry. In the previous two videos, we looked at how to write electronic configurations using the off-bow principle, assigning electrons not just to principal quantum shells, but also to the subshells within those energy levels. So if you haven't any idea of how to do that, do watch my previous video. So in this video, we'll be looking at even more detail of electronic configuration. We won't just be assigning electrons to subshells, but to orbitals within those subshells. So how do we do that? We'll start with a simple example of a nitrogen atom has a proton number of 7. So the electronic configuration for this would be 1s2, 2s2, 2p, 3. So within these subshells, we have orbitals. Now an s subshell has one orbital, and we know that it has a spherical shape. And we know that a p subshell has not just one, but 3 orbitals, and they are all shaped like hourglasses along the x, y, and z axes. So how do we assign electrons to orbitals within subshells? Well, we use a notation known as the box notation. All right. So in this box notation, we have placed the subshells from the lowest energy level for the 1s all the way up to the highest energy level subshell, which is 2p in the case of the nitrogen atom. So as you move up, you have increasing energy level. So we know that the 1s subshell has just one orbital and has 2 electrons. So within this box that represents an orbital, we will place the number of electrons within it. Remember, an orbital can only hold 2 electrons at most. Now these 2 electrons are represented by arrows. So we have a half-headed arrow for 1 electron, and then we have a half-headed arrow for the other electron. Now these 2 arrows, you can see one is pointing up and the other is pointing down. Now there's a reason for this. The reason is that electrons, even within an orbital, are pretty close together. So close that they tend to repel each other. And to minimize the repulsion between electrons in an orbital, they need to have opposite spin directions. So these have opposite spin directions. And these opposite spin directions are to minimize repulsion. And this repulsion is minimized by keeping opposite spin directions for electrons in this same orbital. This rule, or this principle of assigning these opposite spin directions, is known as the Pauli Exclusion principle. So this is the Pauli Exclusion principle. All right. Now in the 2s subshell, we have one orbital, has 2 electrons, both of them with opposite spins to minimize repulsion. Now in the 2p subshell, we have 3 electrons, and these 3 orbitals can hold a combined total of 6 electrons, but we only have 3 in the case of the nitrogen atom in the 2p subshell. So what happens is, you have 1 electron in this first orbital, 1 electron in the second, and 1 electron in the third. Now this placement of electrons one by one in each orbital is to minimize repulsion. Surprise, surprise. So this rule of occupying orbitals with 1 electron each before filling them up with their second electrons is known as Hund's rule. So write this as electrons will occupy orbitals of the same subshell singly. Singly means one electron in each orbital before being filled with their second electrons. So this is basically known as Hund's rule. So according to Hund's rule, we have placed electrons, one in each of these three orbitals. So the electrons are occupying these three orbitals singly before they get to be filled with their second electrons in each orbital. So this is the nitrogen atom. Another example is the oxygen atom. It has a proton number of 8. So its electronic configuration is 1s2, 2s2, 2p4. So when we assign electrons to orbitals within these subshells, so 1s and 2s are pretty much the same as for nitrogen. The 2p is slightly different in that we place one electron in each of the three orbitals within the same 2p subshell that are at the same energy level, and now we have one extra electron. This will go into the first orbital of the 2p subshell, and it needs an opposite spin direction as per the Pauli exclusion principle. We have these two orbitals in the 2p subshell that are still occupied singly, that is occupied by one electron each. So electrons have been assigned to orbitals or boxes within the subshells within the principal quantum shells. So if an electron wants to move out and see the world, that is, move to another principal quantum shell or another subshell, then unfortunately a force called nuclear attraction will put it back in its place, and it will need something called ionization energy in order to actually escape the pull of the nucleus, and that's a topic for another video. So we will sum it up with a past paper example. So we have a silicon atom over here. So it says complete the diagram to show the number and relative energies of the electrons in an isolated atom of silicon. Has a proton number of 14. So it says atom, it means 14 electrons. Now 2 of the electrons have been assigned to the 1s subshell. All right. So before we fill up this diagram, write the electronic configuration as 1s2, 2s2, 2p6, 3s2, 3p2, right? So count the number of electrons that you've assigned, 2, 4, 10, 12, 14. So that's correct. So 2s gets 2 electrons in its one and only orbital with opposite spin directions to minimize spin pair repulsion, right? And we have the 2p subshell. Each electron is assigned to its own orbital amongst the 3 over here before each orbital gets a second electron with the opposite spin direction to minimize repulsion within the orbital. And then we have the 3s, which has 2 electrons with opposite spin directions, and then we have 3p2. Now remember, because it only has 2 electrons, we will place 1 electron in the first orbital one electron in the second orbital, these will occupy these two orbitals singly, that is one electron per orbital, before being filled with the second electron for each orbital with the opposite spin direction. Now this orbital is going to be empty, and so is this 4s orbital because there are no more electrons to be assigned. All right. So in this video, we covered the boxes notation. So this is the boxes notation. So in the next video, we will be looking at that concept I hinted at earlier, ionization energy, the energy an electron needs to actually escape nuclear attraction. It's the energy it needs so that it can finally escape the box or the orbital it is held up in and go out and see the world. So I hope you enjoyed this video. If you did, do leave a like, subscribe to the channel. Inshallah, I'll see you in the next video.